Okay, welcome back for this last part of the TAPAS closing event. And we will start right away with Viviana Mendoza, who will talk about a new virtual articulation therapist. Viviana, the floor is yours.
Okay, good afternoon, everyone there. I cannot see your faces, so it's a pity, but thanks for being there and for joining me in the presentation of our study of a virtual articulation therapist. Yeah, we start this project within the frame of TAPAS and in the work package 2 of therapy oriented. So we try to use newly emerging speech processing techniques to produce automated speech therapy tools that could make speech more therapy more accessible and individually targeted, because there is evidence that increasing therapy, it's also improving the chances of recovering after traumatic events or strokes or surgeries. And so the goal was to develop a virtual articulation therapist that guide the patient through an intensive treatment program for improving articulation and consequently speech intelligibility. And our expected results was a first version of a new software program and the validation on end users. Concept, we have the VAT, that is a tool for segmental articulation therapy oriented for patients with dysarthria, and that includes a well-designed corpus of exercise, specifically target for different sounds. The program is supposed to use algorithms for articulatory error detection, and it's also meant to give auditory and visual cues as well as feedback. But to arrive to this program, this is just a concept, but we first need to answer several questions like why a virtual therapist for subjects with dysarthria, why virtual, why articulation, and what's the feasibility and effectiveness of this intensive articulation. What are the algorithms that are out there, new, emerging, and that are for precise and reliable phonological error detections? Do they need modifications? For our purpose, we focus mainly on Dutch speakers with dysarthria. Which prediction models can objectively estimate the degree of phoneme distortion in this group of patients, and what's the feasibility of a virtual therapy and the end user's acceptability, usability, and interaction with it. So our first study, like a general background, we know that dysarthria involves weakness, slowness, and coordination in the speech musculature, which cause problems in intelligibility. And this has a psychosocial impact, negative mainly, in the person affected with this disorder. And we know from the research that imprecise speech sound articulation is a hallmark in dysarthria, so it's present in every type of dysarthria, independently of underlying pathophysiology or neurologic impairment. Reduce articulatory displacements and lead to reduced acoustic contrast, which is translated also to reduce speech intelligibility. From previous studies from our Professor Mark Devot and colleagues, we also know that intelligibility as a combination of different speech dimensions, like voice quality, articulation, nasality, and prosody. Articulation was the one having the major impact on intelligibility. Therefore, improving articulatory skills, it's often a major goal of treatment for all dysarthric patients. So that's the reason why articulation therapy. And there are several types of behavioral treatments for articulation, and within them we have indirect methods focusing on the suprasegmental level of the speech, like as these methods are well recognized and well accepted because they're almost immediate effect on intelligibility and articulation, but they are meant to compensate for the impairment instead of reducing it. So we try to we try to develop our program for direct focus on the segmental level of a speech, which is intended to explode and develop all available or remaining motor skills, to develop them and to exercise them in order to improve a little bit the impairment instead of compensating it. But there is limited evidence on the short-term effect of these direct methods in speech intelligibility. So this is the first study we did to see how was the impact of direct methods on intelligibility. Why articulation therapy virtual? Well, there is scientific and clinical evidence that improving articulatory skills demand intensive and frequent therapy. This is also in agreement with the principles of motor learning, but current treatments are mainly limited in time to the interactive session in the presence of speech and language therapists. So an automatic or e-health therapy would overcome these limitations. So the virtual therapy has several gains, like to practice more intensively and frequently, to reduce the number of fatiguing and time-consuming transfers to the rehabilitation centers, and to have access to the speech therapy in their home environment. So the first study, like I mentioned, was to see the feasibility and effectiveness of this boost articulation therapy on intelligibility. And for that, we have a pre-post test design study in which 7 subjects with mild to severe dysarthria participate in a program, in an intervention program that was designed like with different levels of severity, yeah, like not increasing the difficulty of the task, and also different types of feedback. And for that, we use 5 sessions of 45 minutes during 1 week, after which 5 speech tasks were perceptually and acoustically evaluated. And for the acoustic, we'd use the formal centralization ratio. The results of this first study show that in the first graph on the corner, showed that there was an increase, a significant increase of mean group intelligibility pre and post therapy. These results are only at phoneme level as an illustration, but we saw that there was an increase in the different 5 speech tasks. This was supported by the acoustic analysis with a reduction in formal centralization ratio. And we also observed that in the different levels of severity, so for mild participants with dysarthria, with severe, moderate and severe participants, they all have a positive effect. The therapy was with a positive effect in intelligibility. So we can conclude that the BAR boost articulation therapy successfully improve articulation and intelligibility in patients with dysarthria at different levels of the speech impairment. Therefore, we could start thinking, okay, we can transform this therapy to a virtual tool. And for that, the first we need was a reliable phonological error detection algorithm. For this algorithm, we select one developed by our colleagues in Erlangen, Juan Camilo and colleagues, and we did modifications regarding to the Dutch for Dutch specific phonological characteristics, and we trained the models with the corpus spoken Dutch, which is a Dutch corpus of healthy speech. And we use recurrent neural networks, and we have 16 phonological features that are supposed to be sufficient for evaluating the phonological errors if they are present. The features or the phonological features are based on the place of articulation, manner of articulation, and voicing characteristics. And the performance of the models is shown in the table. We see that for almost all the phonological class, we have an F score quite good, so which means that the algorithm is accurate enough to detect possible errors during production. In the graph, we can see like a model, what was supposed to the phonological features that were supposed to be present, and a patient production where we don't see. So it was a mistake that the participant did not produce the plosive like it was supposed to be. So once we train it on healthy speech, it's supposed that the system detects possible errors or omissions or phonological errors that can be present. So from this study, we can conclude that the algorithm performance for phonological error detection is accurate and contributes to adequate feedback of uterine production and detailed information. It's difficult to detect and quantify by the human ear, so therefore we have a tool that will do this objectively without the need of human judge. So we wanted to move a little bit further because these results were based on the feedback that we can use from this part of the study. It's like for a feedback on production, but we wanted to give also feedback on results, which led us to the development of a model to objectively estimate the degree of phoneme distortion in subjects with dysarthria. Why phoneme distortion? Because from all the articulatory error types in dysarthria, speech sound distortion is one of the most predominant in this group. So we use 35 subjects, also with mild to severe dysarthria. 3 speech language pathologies scored the target sound from in a visual analog scale, 0 being correct production and 10 severely distorted. 21 target sounds were included, so most of the sounds of the Dutch language. And for the model, we used the phonological features from the former study, but also we did the phonological log likelihood ratio of each phonological posterior of phonological class, a mean of this, because we have it per frame, so this is a mean of the phoneme that was manually segmented, and we end up with a vector of 15 phonological features per phoneme. And we used like an articulation model, classification system, an ensemble classifier, and we divided the data in 4 categories, from non-distortion to severe distortion. And we use also augmented data to have more representative categories. From this study, we can see that the ensemble classifier has an accuracy of 73.5% in general. Specifically for non-distortion to severe distortion, we can see in the confusion matrix, and this would give us a response for patients like based on results on the production, and we can conclude that the classification of sound distortion with the phonological features that we use has a good accuracy, even though we have to refine the models and to improve them. But this is a step forward or toward an automatic score of the degree of phoneme distortion. And it's an appropriate response for patients, for the patients, which contributes to an adequate feedback on results. So we would include in the system feedback on production and feedback on results. This part was not included yet in the pilot study for the evaluation of the tool, so we will not have it now in the demo that I will further present, but this is something also to include and to improve in the final system. Okay, this led to the implementation or the final implementation of the virtual system and the evaluation of the acceptability, usability, and interaction of end users with it. The therapy tool was also evaluated by 14 subjects with mild to severe dysarthria after 2 therapy sessions of 45 minutes. They evaluated with a self-designed questionnaire for and the therapy tool has a first screen where the patient can select the target sound that he needs to train. It has different levels of difficulty also, but we will see that further. And then after he selects the sound, the speech therapist will give instructions in the correct production. So these are already visual cues, and the participant will also have auditory cues and a big set of exercise, well structured and hierarchical, organized for the training. So he will still have here other visual cues, and he can go back to the instructions of the speech therapist, and he select the level of difficulty that want to train, the audio, like the production, the correct production that he needs to follow, and he can also listen to his own production after the results are in the screen. And yeah, I want to show you a small demo of how the system works, but it's mainly this, given if the phonological features were present or not in the production of the patient. Sorry that I didn't add subtitles, so it will be in Dutch. And I want to also thank to our speech therapist, Margot Boudelet. She's there within the participants today, and it's the first time that she will see herself in the big screen. So thanks, Margot.
Welkom bij de virtuele articulatietrainer. Met behulp van dit programma kan u de nauwkeurigheid van uw spraak verbeteren. Het verbeteren van spraak vraagt veel herhaling en doorzettingsvermogen. De feedback die u krijgt helpt u om uw spraak stap voor stap te verbeteren. De oefeningen zijn onderverdeeld in verschillende moeilijkheidsniveaus. Daarnaast komt de doelklank in verschillende posities aan bod. Veel succes!
This meeting is being recorded.
Tijdens de volgende oefeningen focussen we op de klank s, zoals in, sap, massa, roos. Sap, massa, roos. Plaats de tongpunt net achter de onder- of boventanden en laat de lucht naar buiten stromen zonder je stem te gebruiken. Sap, massa, roos.
Saar.
Saar. Saar.
Sik.
Sick. sick. Okay, that was the small demo. After the applied questionnaire to the participants, they all showed being positive, like they were positive toward the use of the virtual therapies. They found it easy to use with a very user-friendly interface, and they could use it independently and in their own environment. That was one of the more important things, that they could continue therapy at their own time from home. So the initial implementation, we can say that it's well accepted and it needs further improvement, but it's in the good track already. From this study, we can conclude that automatic boost articulation therapy is feasible and well accepted by end users, and it's an appropriate solution to increase the frequency and intensity of practice, and it supports the traditional methods of speech therapy. As a general conclusion, we can say that the development of the articulation therapy is a unique and well-designed structured therapy program for intensive and direct articulation therapy based on the principles of motor learning, that it's feasible and well tolerated by the patients, and both the perceptual and objective outcome measures of the of the boost articulation therapy show positive results on intelligibility with a significant improve in patients with chronic and progressive dysarthria at different levels of the impairment. The algorithm for the Dutch-specific phonological error detection chose to be accurate. The automatic model for the objective classification of phoneme distortion from the for a specific target sounds also, it has a good accuracy. The development of the patient-friendly interface for the virtual therapies was also accepted by the end users, and it provides a set of exercise, visual and auditory modeling of the target utterances and an adequate feedback with accurate performance. The visual feedback within the virtual therapies was found to be attractive, clear, and easy to interpret. So that was our study. Thanks for your attention. And if you have any further question, please.
Thank you, Viviana, for your excellent presentation. I will give the microphone to Margot, who's going to do the Q&A. Yes.
The Q&A, yes. Are there any questions in the audience? Yes, there is one.
Hi, Viviana. Thanks for your presentation. You mentioned something about augmentation. Could you maybe tell us something about that? And the screen is frozen. Hello?
Oh,
Okay.
it's her.
Maybe Greg, you can answer those questions. I think it's a 4 o'clock problem.
Is haar internet weg? Oh.
She's not anymore there. Oh. Yeah, Lucas. I'm not really prepared. Was not prepared. In the data augmentation. Yeah. Okay, sorry. I try to remember though. It's yeah, but she told me earlier that she had internet until 4. So yeah. So I don't expect her back. Yeah. No, but yeah. Okay, she will be back. There's no one waiting. Yeah, okay. Ja. Nog eens meer. Nee. There's no one. Lynn, any news from her or? But eventually. Okay, we give it 2 more minutes and then we just, yeah. Okay, thank you. Yeah. Okay. Yeah. And are there any questions about the tool itself or?
Hello, I think I'm back again. Oh my God, sorry.
Okay.
I was suddenly out of the system. I didn't want to avoid the questions.
But there was a question for you. Lucas was asking about the data augmentation for the distortion score. So could you give us some more information about that?
Yes, of course. I did data augmentation with MATLAB. I didn't change anything related with timing. So I only add a little bit of noise, a little bit of change of frequency, and also volume, like amplification of the signal or diminishing a little bit. And that was randomly and sequential. So with the probability, I have the details somewhere that I can show you. But it's that enough, or do you want to see a little bit more of detail?
It's enough. Thank you, Viviana.
Okay.
Other questions for Viviana? Yes.
Hi, hello. Thank you for the presentation. I was just wondering, do you plan to add any other exercise in the virtual assistant?
Yeah, in the future, we would like also to go a little bit to sentences or phrases more than the just words. But yeah, that's something that needs to be also a study first. Even running a speech could be for future research, but yeah, at present it's only word-based.
Okay, thank you.
Yes. Yeah, Viviana, I think that the virtual articulation therapist is now doing what we were thinking from the beginning. So, but on the other hand, you never can have enough material to have your patient practice. So I think really there is a need to add more exercises and more words and more audio samples and examples. So it's not that the tool is finished. So it would be nice if we could find the resources to, to expand it more. Yes.
Yeah, and I also need to include the final study that was for phoneme distortion that was not there for the pilot study. So that's another thing that needs to be improved in the system.
I just have one question. Maybe I missed your presentation. So you did an evaluation at the user level. I was
Yes.
user here is the patients in this case. So I was curious to see if you did a study to see the other user, which is the SLP, the speech and language pathologist. How did they feel about this application?
We didn't include any speech pathologist or family members or anyone. So that's also would be nice to investigate. We only develop it within the group of the hospital. So yeah, it needs to be presented and extended for other hospitals and clinics, and yeah, to see also an evaluation of how the speech therapist feel with the program.
Yeah, because adoption point of view, it will be whether the speech language pathologist say, hey, please adopt it. It will help you to even recommend that, we need this. But this is really already a good work. But I was wondering, the other side was looked at, because application point of view, it has to be coming from the speech language pathologist side as a recommendation. Or if, for example, suppose tomorrow we want to cover this through an insurance system, then it will have to come through that other side. As an application, it can go, but the other side will be needed. So thanks for that.
Yes, of course, we want to include, because also they can have also more input about what we can change or what we can add more or what it's more necessary. But at this point, we only have like the feedback of the end users, and I think that's quite important, or was quite important for the development of the system, to see if they felt comfortable, if the system was not too complicated, because sometimes those participants have also brain damage and they cannot handle really difficult programs. So we wanted only to, at that moment, to know how they feel about working with the system.
Okay, thank you, Viviana.
Thank you.
Yes, there was the idea of Julie of taking a picture of with everyone online on the screen in the auditorium. Do you still have 5 minutes, Viviana?
Yes.
So, and then we will ask everyone in the room here to come closer. Okay, and then can I ask everyone online to put their camera on? It's all on the